In this video, we'll be discussing physical quantities. A physical quantity is any physical property of a material or system that can be quantified. There are 7 fundamental quantities in physics. The 7 fundamental quantities and their SI units are mass, measured in kilogram, length, measured in meter, time, measured in seconds, electric current, measured in ampere, thermodynamic temperature, measured in Kelvin, luminous intensity, measured in candela, and lastly, quantity of a substance, measured in mole. Derived quantities, on the other hand, are defined in terms of the 7 fundamental quantities. Their units are obtained by combining fundamental units. Some examples are velocity, measured in meter per second, force, measured in Newton, and pressure, measured in Newton per meter square. Apart from classifying physical quantities into fundamental and derived quantities, we can also classify them into either scalars or vectors. Scalar quantities are quantities that can be described completely by their magnitudes without directions. Examples are mass, area, volume, density, and temperature. Vector quantities are quantities that can be described by their magnitudes and directions. Examples are displacement, velocity, and acceleration. We can represent a vector by using a line with an arrowhead at its tip. The length of the line shows the magnitude of the vector, and the direction of the arrow shows the vector's orientation. Any vector can be completely described by its components. A component is a projection of a vector along an axis. Let's consider a vector A lying in the xy plane and making an arbitrary angle theta with the positive x-axis, as shown. AX is the component of A along the x-axis, and AY is the component of A along the y-axis. From the definitions of sine and cosine, we see that cos theta equals AX over A and sine theta equals AY over A. Hence, the components of A can be written as AX equals A cos theta and AY equals A sin theta. These components form two sides of a right triangle with a hypotenuse of length A. Thus, we can represent the magnitude and direction of the vector A in terms of its components. We can write its magnitude as the square root of AX squared plus AY squared, and its direction, theta, as the tan inverse of AY over AX. The direction of a vector is usually stated in terms of the positive axis. In the first quadrant, AX points right and is positive, while AY points upwards and is positive. In the second quadrant, AX points left and is negative, while AY points up and is positive. In the third quadrant, AX points left and is negative, while AY points down and is also negative. Finally, in the fourth quadrant, AX points right and is positive, while AY points down and is negative. Let's now move to the parallelogram law of vector addition. This law allows us to represent the resultant of the vectors A and B in magnitude and direction as the diagonal C of the parallelogram formed by both vectors. We can then find the magnitude of the resultant of both vectors as the length of diagonal C using the cosine, which is given by C squared equals A squared plus B squared minus 2AB cos theta. We can also find the direction of the resultant vector using the sine rule. The sine rule is given by sine theta over C equals sine alpha over A. Let's now see how we can use the parallelogram law of vector addition to find the resultant of two vectors. Let us consider we have two vectors, both of magnitude 100 Newton, and inclined to each other at an angle of 130 degrees. Our first step would be to draw a parallelogram whose sides are represented by both vectors, and then our resultant vector as the diagonal of the parallelogram. We can now calculate the magnitude of our resultant vector by using our cosine rule, where A and B represent the sides of our parallelogram, which have values of 100 Newton, and our angle theta is 50 degrees. We use 50 degrees instead of 130 degrees because 50 degrees is the angle facing the resultant or the diagonal in the parallelogram. So plugging our values into our cosine rule and solving for r, we have r equals 84.52 Newton. We can also calculate the direction of our resultant vector with respect to one of the vectors by using our sine rule to solve for the angle alpha. So substituting our values into the sine, we find alpha as 65.01 degrees. There are two kinds of multiplication of vectors, namely scalar product, also called dot product, and vector product, also called cross product. While the scalar product of two vectors yields a scalar quantity, the vector product of two vectors yields another vector. The dot product of two vectors A and B can be expressed as the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between both vectors. The magnitude of the cross product of two vectors A and B can be written as the magnitude of A multiplied by the magnitude of B multiplied by the sine of the angle between both. To demonstrate how we evaluate dot and cross products, suppose we have two vectors A and B as shown. The dot product AB is given by AXBX plus AYBY plus AZBZ, and the cross product of vectors A and B is given by the determinant shown.